Okay, so this mini lecture is going to look at a few things. First, we're going to recap polarization really quickly, and then look at a mathematical representation for polarization so that we can actually calculate the intensity of the light that goes through a polarizer and then a subsequent, what we'll call analyzer, so two polarizers. We will also look at an example problem using that mathematical relationship. And then I'll talk at the end a little bit about polarized sunglasses and how they work and why we would want to use polarized sunglasses, especially those that like help us with fishing or driving at night. So what's special about those and how might they help us in our visual acuity in those situations. Okay, so polarization, real quick recap. There's a great conceptual video on this. Make sure you're looking at that to get kind of the big ideas. But let's recall from that video that polarized light is really a orientation of light in a specific direction. So light beam from like the sun has polarization directions in all sorts of different directions. Okay, and that polarization direction, remember, is the direction of the electric field wave in our electromagnetic wave of energy. And when we put this unpolarized ray of light, like coming from the sun, through a polarizing film or filter, a polarizer, we'll call this one our polarizer, when we put it through that, these are like that picket fence where only the energy with orientations, let's say vertically, we'll use a vertical filter here in our example, only the energies with orientations that are vertical are going to get through. So if we imagine any one of these beams of light, they can have two components of that polarization direction, a horizontal component and a vertical component. So when only the vertical energies are allowed through, then we have a polarized beam of light whose orientation is the orientation of the polarizing film. In this case, this plain polarized beam of light is vertical. Half of the energies have gotten through. Again, if we think about this, the polarization directions that are present there, they have horizontal components and they have vertical components. Every one of those polarization directions can be broken into a horizontal or vertical component. And so when I put a polarization that's purely vertical, for example, we get about half the light. So the intensity of this polarized beam, I'll say I sub P, is equal to the original intensity of that light times half. I've cut it in half. It's half the original intensity of the light. Well, we saw in that demonstration in that other video that if I put another polarizing film, and I'm going to call, I'm going to call this the analyzer. Okay, so if I put another polarizing film and analyzer at some orientation relative to that first one, only certain energies related to that orientation are going to get through this polarized beam. So like in that demo, if I put a vertical analyzer there, the vertical beams get all the way through, and we don't see any change in intensity. If I put a horizontal analyzer in front of this polarized beam, then nothing is going to get through because all I have is vertical energies here. Only horizontal energies would get through a horizontal analyzer, and therefore it's black. And some relative amount of polarization, of that polarized beam, some relative intensity gets through depending on the orientation of this analyzer with respect to that polarized beam. And it's that mathematical relationship that's known as Malus's Law that tells us what is the intensity of the light on this side coming through this analyzer relative to the initial. And so Malus's Law tells us that the output, the intensity on the outside, the intensity here at the end, is equal to the intensity of what goes into that film times the cosine of the angle, and that whole thing squared. So the cosine squared of the angle. And this angle is important. This is the angle between the analyzer and its orientation and the polarized beam. Okay. So this is what's known as Malus's Law. And we're going to use that to determine what is in fact the intensity, and we can also talk about the orientation, the intensity of a light ray that passes through an analyzer. Now, I'm using this word analyzer. It's just another polarizer. It's just another polarized film. But to distinguish between first that polarized light film that we took to get our unpolarized ray through in a certain orientation, and then the analyzer is that second polarized film. So I'm going to use two different words to help distinguish it. But the reason that we call it an analyzer is because we can actually use it to analyze whether a ray of light is actually polarized or not. If we have a polarized beam, then this analyzer can be rotated to identify the orientation of that polarized beam of light. Any other orientation will vary from the full intensity, so the same orientation, to darker. So if I look at a polarized light through an analyzer, I can rotate that analyzer to determine the direction of polarization of that polarized beam. Or I can determine if it's polarized at all. Does it change as I rotate it? If I had this film and I rotated that polarizer in front of an unpolarized beam of light, I don't get any difference in the intensity because it's unpolarized. If I do the same with a polarized beam of light, I do. And so that's why we can use it to analyze. So I'm going to use those two languages. We're going to do an example problem using Malus's Law in terms of the intensity. So what will that example problem look like? Let's imagine that I have an unpolarized beam of light that I put through a vertical polarizer. And then I take that vertically polarized beam of light and I put it through an analyzer that is orientated at 60 degrees with respect to the vertical. What is the intensity and orientation of the beam of light on this side after it goes through the analyzer? All right, so we first have an intensity, and we'll do that intensity relative to the intensity of the unpolarized light. So we're going to call the unpolarized light intensity naught, okay, our initial intensity. What will be the intensity of the light after it goes through the first polarizer? Remember, it cuts the light in half. And this is vertical, so it's cutting out all the horizontal energies. So the intensity through that first polarizer, we'll say intensity P, is equal to 1/2 intensity naught. Okay, half the intensity of the original light. Now we're going to use Malus's Law to determine the intensity through this analyzer that's orientated at 60 degrees. So looking at Malus's Law, we want to know what is the intensity of the light I'm interested in. I'm just going to call that I. That's going to be equal to the intensity in, which is the light coming in, is my polarized light, times the cosine squared of the angle between the analyzer and the polarized beam. I know that that polarized beam is a vertical. I've said that this is 60 degrees with respect to the vertical, so this is 60 degrees. All right, well, the cosine of 60 degrees is 1/2, and if I square that, I get 1/4. So I know the cosine squared of 60 degrees is 1/4. My polarized beam is 1/2 I naught. And so I find that the intensity of my final beam is 1/8 the initial intensity. So the intensity is 1/8 the initial intensity. What orientation is that polarized beam on this side? Well, my last filter was at 60 degrees, so this is at 60 degrees with respect to the vertical. All right, so using Malus's Law to actually calculate the intensity of light that we get out. And of course we can use that same law to say if I want to reduce my light by 30%, what orientation of film do I need to have with respect to the polarized beam coming in, for example. So we can use it in a lot of different ways. Now, how does this work for polarized sunglasses? Well, it turns out that polarizing film is one way that we get a polarized beam. Reflection is another. We actually, when light is reflected, it can be reflected in such a way that the reflected light is polarized. So if you imagine light hitting water, some of that light is transmitted through the water. It bends due to refraction. We'll get to that in a different video. but some of that light is reflected. And it turns out that a lot of that light is reflected horizontal to the surface. And so in the case of water, that's Earth horizontal. And so therefore it is reflected with a polarization that's predominantly horizontal. So if I take sunglasses that have polarizing lenses in them and I orientate them in a certain angle with respect to the horizontal, I can get a very defined intensity reduction of the glare that's coming off of the lake. Depending on how strong I want that intensity reduction would encourage me to build my sunglasses with varying angles. Okay, so I might have one for real intense and one that angle is less intense for the intensity that I'm trying to get to. If you have a pair of polarizing sunglasses, try this out, because the other way to do it is just to rotate those sunglasses. Obviously, you can't wear them when they're rotated, but you can see the effect. That if you have polarizing lenses and you look at the surface of the water, for example, if you rotate those sunglasses, you will see that it'll either get darker if it's going further away from that polarized direction, or it'll get lighter if it's getting closer to that polarized direction, that horizontal. So kind of a fun way to think about your polarized sunglasses. All right, so looking at Malus's law, looking at polarization from a more mathematical perspective. And again, if you want that conceptual description, by all means, go check out that video on polarization. Good job.